In the last lecture, we saw the notion of hypercontractivity and saw how it can have amazing consequences in terms of strong data processing inequalities. And in fact, there are many more which we did not discuss. We saw different equivalent forms of hypercontractivity. And the question is this really a new phenomenon which has not been seen before? And what we will now see is that, in fact, for some distributions like Gaussian distributions, hypercontractivity is exactly equivalent to log Sobolev inequality. So before we proceed, let's just first describe Gaussian hypercontractivity. Okay. So we consider generic Gaussian random variable pxy. Let xy be jointly Gaussian zero mean random variables. Okay, what does it mean? That is, pxy is Gaussian with mean 0 and covariance matrix K with K given by, let's also assume that they are standard normal, so we normalize them to unit variance, and rho is their correlation coefficient. Okay, such xy can be expressed as, this is something that you may know already, y equals to rho x plus root 1 minus rho square z, where z is independent of x and it's again zero mean and unit variance. Note that x and y are both zero mean and unit variance Gaussian random variable. Okay, so here is this Gaussian hypercontractivity theorem from to Gross. It says that pxy perv is pq hypercontractive if and only if q minus 1 by p minus 1 exceeds rho square. Okay, this we don't even claim by the only if part. If this exceeds rho square. In other words, the quantity spxy that we had seen is exactly equal to one plus p minus 1 rho square by p. Okay, not an easy form to remember. I think this is an easier form to remember. Q minus 1 by p minus 1 exceeds rho square. Okay, this is the Gaussian hypercontractivity, and now we would like to prove it. In fact, to prove it, we will develop a little bit of we will use a little bit of heavy machinery. Eventually we will do that, but to begin with we will start from some elementary proof. So the proof proceeds as follows. We first recall that by using the equivalence between PQ hypercontractivity and the strong data processing inequality that we saw for linear divergence, it suffices to show that for all Qx that have density with respect to this Gaussian density Px, and such that this density has dqx by dpx to the power be the pth moment finite. What we need to show is that for all such qx, the pth divergence between qx and px when passed through this channel. Okay. By the way, this channel we parameterize by rho because that's what brings in this rho. Remember, this channel can just be described as this additive Gaussian noise channel. It multiplies with the gain rho and this 1 minus rho square. So this is a channel parameterized by rho, and this guy is less than equal to 1 minus q by 1 minus p dq qx px if, or this is true for all p less than equal to 1 plus q minus 1 by rho square. In fact, we use a slightly different parameterization, but before that, this last inequality, by the way, is equivalent to log, this is something we saw earlier also, w rho of p is less than equal to log dqx by dpx. And this is q. And this must hold for all p less than equal to 1 plus q minus 1 by rho square. In fact, it suffices to have it for p equal to this by rho square. Now, just a side remark, we saw earlier that this guy here, the Markov kernel for the channel applied to the log likelihood, to the likelihood ratio, to the density, is exactly the same as this guy. Remember that. Okay. And this is, by the way, the Gaussian density. When you apply this channel to Gaussian input, you get Gaussian output. Okay. Now we will see this thing and we'll use a slightly different parameterization. Writing rho equals to e to the power, this only depends on rho square, so we'll write rho square as e to the power actually we assume rho is positive because otherwise the same proof can be repeated with x replaced with minus x, doesn't change anything. So we set rho to be e to the power minus t, and wt for w rho, what we need to show is that if you look at this function gt, or maybe something else, maybe call it rt, define. So this logs can also, by the way, we don't really need to have these logs here. So it suffices to show that this function rt defined as wt dqx dpx pt. This is the quantity we are calling p, pt, with pt defined as 1 plus q minus 1 e to the power 2t. This quantity here is non-increasing for t greater than 0. Okay. And this is true since w0, what is w0? w0 basically corresponds to having rho equal to 1, and in which case y equals to x. Okay, so this channel is just the identity channel. So w0 is the identity mapping. Okay, that's what we have to show. So let's take the derivative of this function and show that it's less than 0. That's all we need to show. Okay, but how do we differentiate this function? All right. So to do that, to show this, note that Wt of this qx dpx, this is exactly the same as the conditional expectation of dqx dpx. Now this is a function of x. X is the standard Gaussian random variable here, given y. Okay, that's something we have seen earlier. And we should say it's given yt, denoting by yt the random variable y corresponding to e to the power minus t. Okay. But in fact, there is a symmetry in the channel from y to x and x to y. This distribution is symmetric. This distribution here is symmetric. And therefore, this can also be written as expected value. This is bisymmetry. Symmetry of the distribution. So this is since x, y, t has the same distribution as ytx. So this can be written as dqx by dpx. Now this symmetry is actually pretty crucial to this proof, but it holds here. It holds for the symmetric channels. This is this yt given x equal to y. Okay, so this guy has now this kind of trajectory. All right, but so let's abbreviate this Redound-Nikodym derivative. Denoting g of y as, or maybe g of, doesn't matter, x as dqx dpx of x rt is given by expected value of g of yt given x Yeah, so the entire distribution is symmetric, so that we can take the outer expectation with respect to, we can take the outer expectation also with respect to uh, x. Okay, remember that the original thing had this outer expectation with respect to y and the inner one with respect to x. So this is RT. Therefore, so we can write a little bit more about it. This is equal to expected value of, now we know what G looks like given x. Looks like e to the power minus tx plus square root 1 minus e to the power minus 2t z. Okay, and given x, this expectation is over z then, by the way. Given x to the power pt and then to the power 1 by pt. Right. Actually, it will help keeping the log. Sorry about that. Let's keep this log here. Okay. So RT was this. RT is defined as log of this, same thing. And then this guy has a log here. And this also has a log here. Right. Okay. So then, if you take derivative of r with respect to t, so this is this by this. So this expression here, this is equal to, first we take derivative of this 1 by pt, so that's minus, so one convention, when we take derivative with respect to t, we use a dot. Okay, so some convention here. D by dt of gt or any function actually, d by dt of h p is h dot, and d by dx of hx is h prime. Okay, we'll use this dot and prime notation. So here we have p dot t by pt square times, of course, the natural log of expected value of this whole thing, expected value of g by t given x to the power pt. Okay, and plus 1 by pt, and now this second part of the derivative, so log of this, we can get this in the denominator, and derivative of this guy. Now we can take derivative inside, and then there are two terms given x, and we can now focus on this guy. So first term is taking the derivative again of pt, but this guy will remain. Right. So that's expected. So that's p dot t. So just taking in, this is just taking derivatives, plus now we take the term of this guy, p dot t, p dot t. Yeah, maybe it's convenient to use a little bit more notation. So let's call this, name this function something. We'll call this ht. Okay. So what we see is, for the second term, what we see is plus 1 by pt expected value of ht is a random variable, ht to the power pt, no problem. And then in the numerator we can take derivative inside ht to the power pt. What's the derivative? That's e to the power ht log ht pt. So first it's e to the power ht pt, so that's ht pt times, two terms will come. First one is pt by ht into h dot t plus p dot t into log ht. Okay, these two terms come here, and therefore this is minus p dot t pt square log expected value of this ht to the power pt plus p dot t by pt, let's say pt square again, expected value of log, so this is the second term here, this one, so ht to the power pt log, I multiplied and divide by pt, so you have this, and plus this pt cancels here, it's the expected value of ht pt minus 1 h dot t by expected value of this expected value remains here as well, expected value of ht to the power pt ht to the power pt, and we would like to claim that this is less than equal to 0 if p dot t, so there is a, so we multiply and divide this guy by pt square, p dot t times expected value of ht pt log ht pt minus, we have multiplied and divided by this denominator here, ht pt log expected value of ht pt. Okay, this is the first term, plus pt square expected value of ht pt minus 1 h dot t is less than equal to 0. So this term, if you see this term, this exactly look like p dot t into entropy of htpt plus pt square expected value of ht pt minus 1 h dot t is less than equal to 0. Note that for our choice of pt, this p dot t is nothing but, you can show this, is 2 pt minus 1. You can verify this. remember pt was 1 plus q minus 1 e to the power 2t. So you get from this formula, and this must be greater than equal to, in fact must be strictly greater than 0. This is strictly greater than 0, and this implies this previous inequality holds if and only if the entropy of HTPT plus PT square by 2 into PT minus 1 expected value of HTPT minus 1 H dot T is less than equal to 0. Okay, so that's what you have to show. And now that we see this nice entropy term here, this one here, okay, it is time to bring in the log Sobolev view. Let's introduce a slightly more heavy notation. So remember that recall that this HT that we're using here, this HT was given by the conditional expectation of g of yt given x. Yeah, that's what HT was. And right, so this is a function of x basically. So we will now use this slightly heavier notation. Let me call this h t of x. Okay, so that I see this dependence on x explicitly. It depends on t, and it's a function which depends on t, and then it depends on x. Then where x is the Gaussian random variable, x is normal 0 1. Then log Sobolev inequality implies, what would be log Sobolev inequality? It says that expected value of htx, the entropy of htx to the power pt f square minus the gradient of this guy. So what is this function? This is d by, so we are looking at htx to the power pt by 2. What is its derivative with respect to x? It's pt by 2 into htx to the power pt by 2 minus 1 into htx prime. So this is the derivative with respect to the argument whole squared. This is log Sobolev inequality, and this is the inequality we want to show. So let's number this guy. Let's call this some hash. Thus hash is equivalent, not equivalent, then hash follows from log Sobolev inequality if, so we'll add and subtract this term. So this term must equal this term. Okay, so this plus this should be 0 if minus expected value of So we'll take this out. Pt square by 4 htx pt minus 2 ht prime x whole square equals to this term now, pt square by 2 pt minus 1 expected value of ht pt minus 1 htx pt minus 1 h dot dx. So if we show these two are equal, then this will follow from Log-Sobolev inequality. And in fact, the opposite implication, the fact that Log-Sobolev inequality follows from hypercontractivity, also can be shown similarly by somehow using a t for which this function becomes your required function. Okay, so we will not discuss that part. We'll just talk about this part of the implication. Okay, so how do we show this now? This is what it has come down to. So this holds if and only if, log-Sobolev inequality at a factor of I think there's a factor of 2 that I have to bring in. It is my factor. Right, this is the log-Sobolev inequality. So this guy here will be just by 2. Okay. So this holds if and only if this guy here, expected value of htx to the power pt minus 1 h d by dt of hdx is exactly equal to minus 2 pt minus 1. Expected value of okay, that's what this formula is what you have to show. So that's what you have to show. Now, in showing this formula, we will use a little bit of heavy machinery. Okay. So till now, I think this was an elementary calculation, and the big observation here is that these two quantities are the same. And once we show that, we are done. Our proof is complete. So to show this, we develop we recall some basic concepts from the from continuous time Markov chains. Okay, so we'll call this, we'll number this inequality. This is this identity. This is 1 for us. We'll show this. Okay. Okay. So a Markov process can be described by its maybe we describe only in the context of the process that we work with. So for us, this yt is given by e to the power minus t x plus 1 minus e to the power minus 2t z, where z is a Gaussian noise, and x can be any random variable. We start with a Gaussian x, uh, but in general we can start with any other x tilde. Okay, this is the process we are looking at. So in fact, this process can be viewed as follows. So consider this random variable yt and apply, look at yt1, consider yt1 and let y prime be given by e to the power minus t2 yt1 plus minus t2, let's call it z prime, which is an independent Gaussian noise, independent of everything else in the past. So this becomes e to the power minus t2 e to the power minus t1 x plus 1 minus e to the power minus 2 t1 z plus square root 1 minus e to the power minus 2 t2 z prime, and this is equal to e to the power minus t1 plus t2x plus e to the power minus t2 into root 1 minus 2 t1z plus root 1 minus e to the power minus 2 t2 z prime. So if you look at this guy here, this is again a zero mean Gaussian random variable here with variance. So its variance is given by, so let's call this guy z prime prime. So variance of z prime prime equals to expected value of z prime prime square, which is just the sum of these two variants because these two are independent. So it's e to the power minus 2 t2 into 1 minus e to the power minus 2 t1 plus 1 minus e to the power minus 2 t2. So that's 1 minus e to the power minus 2 t1 plus t2. Okay, that's the variance of z prime prime. This whole thing is what I'm calling. So essentially, I can view this random variable here as this is equal to e to the, so y, this y prime is equal to e to the power minus t1 plus t2 x plus square root 1 minus 2 t1 plus t2, and then there is a random variable which is independent of x and is normal 0, it's Gaussian 0. Okay, thus y prime exactly is equal to, has the same distribution as y t1 t2 t1 plus t2. So this process actually, if you can, from this you can sort of convince yourself, this is just some quick heuristic calculation, that this process is a Markov process, and therefore it has a semigroup linear operator associated with it, which is given by the following. Let wt, this name is not important, that I'll just define this operator. Wt of f is of x is defined as the conditional expectation when you run through this Markov chain of f given x equal to x, and this operator captures this operator w2. Okay, so this operator w2 is a mapping from all, I think, functions with finite expectation to again functions with finite expectation. Right. So this W2 actually captures the evolution of the Markov chain. And in fact, there is another operator that one can one can associate with the Markov chain. It's the generator, or the, let's say, the sometimes called the infinite decimal generator, associated with WT. Let's denote it by L, is given by so this guy L again acts on the same functions, is given by, if you take WT of a function and you take its derivative, then that is equal to, almost surely equal to, WT of L of f. Okay, which is also the same as L of WT of f. There's an operator which will satisfy this equation, and that's this infinitesimal operator. Okay. Actually, a better definition of this L of f is the following. L of f of x equals to is defined as, so I'll define it for every x, limit t going to 0, d by dt of WT of fx. Okay, so this guy, this is maybe a better definition. This can also be treated as a definition. The operator for L should be L and WT are related through this equation. This is sometimes called Kolmogorov's equation, but perhaps this is a better definition. Okay, so you can associate this generator matrix with it. Right, it's telling you how the distribution is changing per time. Roughly, that's what it tells you. Okay. Now, this operator has some very nice properties. Okay. So firstly we can find this operator associated with our own continuous prime Markov chain. So for us, for our Markov chain, let's try to compute this derivative. WT of f of x is equal to conditional expectation of f of yt given x equals to x, which is equal to expected value of f of e to the power minus t x plus square root 1 minus 2tz, and that's just WT of x, and therefore t by dt of WT fx equals to, so you can take this derivative inside. So first you'll get this x part, so it's expected value of f prime to the power minus tx plus square root 1 minus 2t z, and then the derivative of this part with respect to t. So that's given by e to the power minus tx plus, what's the derivative of this part? That's e to the power minus 2tx by square root 1 minus to the power minus 2tx yeah, so minus minus cancel, so it becomes plus times z. Okay, that's what we get. So this is exactly equal to e to the power minus tx expected value of f prime e to the power minus tx plus square root 1 minus z plus e to the power minus 2t by square root 1 minus 2t expected value of z f prime e to the power minus tx plus okay. So taking the limit t going to 0, actually t goes from 0 from the positive side of this limit. So this one remains as, so this guy as t goes to 0, this becomes x expected value of f prime x plus, oh, this again goes to 1 here. Yeah, actually before taking the limit we will simplify the second term now. So the second term is actually quite interesting. So if you are given any function, let's say h, and you look at this guy here, this is exactly equal to so we'll use an integration by part formula here. So this is Gaussian density minus 1 by root 2 pi z h z e to the power minus z square by 2 dz. So let's use integration by parts. So this is equal to 1 by root 2 pi minus infinity to infinity. If you take the integral of this function z e to the power minus z square by 2, then that's just again e to the power minus z square by 2. So you get this and minus, in fact you get minus of this and then plus h prime z e to the power minus z square by 2 by root 2 pi dz. Now turns out that we can restrict our attention to those functions for which so we have this function f here, an arbitrary function f. Turns out by some approximation arguments it's enough to restrict our attention to these functions f which are compactly supported and continuous and differentiable. So they are in fact we can assume that this guy goes to 0 as z goes to infinity. Okay, so this is 0 and what you are left here is expected value of h prime of z. Okay, so we'll apply this formula here. When you take derivative of this with respect to z now, this factor comes out. Therefore, this guy here, d by dt wt of fx, we already saw the first term, that was e to the power minus tx expected value of f prime e to the power minus tx plus this. And now the second term is e to the power minus 2t expected value of f prime prime so in the limit as t goes to 0, this thing goes to x expected value of f prime x, so which is just f prime x, and similarly the second term goes to, I missed a minus sign somewhere. There's a minus sign here, right? So this minus sign is here, plus f prime prime x. Okay, so this gives us the infinitesimal generator matrix for our Markov chain of interest. This particular operator, and in fact, this Kolmogorov equation that I wrote here, it's quite useful. It tells you the derivative of this function is actually the L of that L of that function. And the reason, and I have not derived this formula, you can explicitly verify this formula, by the way, for our case, but this holds in generality. This matrix must satisfy this. It's easy to show this. It's easy to show this formula by just using the fact that by using the fact that this WT of f is, this WT is a semigroup, so WT plus S equal to WTF, and then WS applied to it. Using that, you can establish this formula, but I'm not deriving that formula. And if you really are interested for this specific distribution, for our specific Markov chain, you can verify this formula. The derivative of WT of f is LWT of f. Now, the reason this formula is important for us is because in our calculation, we see this guy here, d by dt of ht of x, where ht of x, if you remember, was a similar conditional expectation. This is basically wt of g of x. So this is the derivative of wt of g of x, and that must be L of t of x. Okay. So I'll name this guy. This is Kolmogorov equation. So for our application, we consider this guy here. So that's expected value of Wt of g of x to the power pt minus 1 times d by dt of Wt of g of x. That's what we look at, which is equal to, now we apply this Kolmogorov equation. So this guy here is pt minus 1 L of Wt of gx, because this derivative is L of Wt of gx. Okay, and this is by once again, you can just verify it by differentiating. Okay, so now what? We have shown this. Now it turns out that for this particular Markov chain, now this is the next thing we will need about our particular Markov chain claim. Expected value of fx L gx for our Markov chain is equal to minus expected value of, actually, first thing, this is true for any Markov chain when x is the stationary measure. Note that x is the stationary measure for Markov chain, because if you start with Gaussian, the distribution always remains to be the same Gaussian. Okay, and for that we must have this. It is true. So this operator L is so-called self-adjoint, and in fact this is equal to expected value of f prime x g prime x. Okay, that's the claim. We will show this, but using this formula above, using this formula, this expected value here, wt of gx to the power pt minus 1 d by dt wt gx, this is the quantity we were looking at here, and this is this. We now have to just take derivative of two things, derivative of wt gx and derivative here. So that derivative is with respect to x. So first we take this derivative with respect to x, that becomes pt minus 1 times the derivative of this guy with respect to x. So wt of gx to the power pt minus 2 times derivative of this with respect to x, which will bring back remember we were not using this notation htx for this, so this notation is more convenient. Sorry, we have to switch between these notations so many times. And so it's derivative ht prime x. This is good, yeah. And then also the derivative of this guy, this is just ht, so derivative of this is again ht, so you get this. But this is exactly what we wanted to show. Okay, so we have shown this, and you can go back and check here. This is same as R1. Okay, so which is the same as 1. So it only remains to establish the claim. So proof of claim. This is true for any fg for our particular generator matrix, for our particular infinitesimal generator here. So first thing we will show is that this is equal to this. Okay, that's the first thing we will show. First, expected value of fx lgx equals to expected value of lfx gx. So how do we prove this? Proof expected value of fx. This is for any fg, not the particular g function that we have above. Wt of some function gx is equal to expected value of fx, expected value of g yt given x, which is also equal to expected value of fx gyt. But note that since these random variables are exchangeable, the distribution of xyt in this case is the same as distribution of ytx. In general, this will be true for a reversible Markov chain. So there we can write it as f of yt gx. Okay, you can, this symmetry we have mentioned earlier also. But then this becomes expected value of wt fx gx. And so now what we do is we take derivative with respect to t and take limit t going to 0. This derivative, I'm taking it inside freely, and that assumes some regularity conditions on this f and g, something like they are compact and continuously differentiable, and all that is true here. So we can take it inside, no problem. So this guy then becomes equal to limit t going to 0. And in fact, again, this limit can also be taken inside, and this implies expected value of fx lgx is equal to expected value of lfx gx. Okay, so this function is symmetric this way. Okay, so then second property. Expected value of L of fx is equal to expected value of 1 times L of fx. This first property didn't really use, the only thing we used was reversibility here. Didn't use anything else. Didn't use the Gaussian assumption. This is exactly equal to, from the previous property, L of 1 times fx. And now we use the Gaussian property. This L of 1 is basically the derivative of, involves derivative of constants, and so this is 0. 0 for our Markov chain. Because Lx is given by this operator here. Both f prime and f prime prime will be 0. So this is 0. And therefore this is 0. So for our Markov chain, L of any fx is, the expected value is 0. So Lfx is a 0 mean random variable. Okay. And now the third step is to apply this property to, so we consider expect 0, which is expected value of L of fx gx. Maybe a better way to write it is the product function f gx. But this, let's write what is L of f gx. That's minus x f g prime plus f prime gx plus fg prime prime. This is equal to minus expected value of x fx g prime x plus x f prime x gx. Okay. Plus expected value of f prime prime x g prime x plus f prime x g prime prime x f prime x gx plus fx g prime prime x plus 2 f prime x g prime x. Okay, so this is exactly equal to, you can simplify this, collect the terms with G and collect the term with F. So this is minus expected value of it's not no minus expected value of, if you collect these terms, fx L of gx plus expected value of gx L of fx plus 2 times expected value of f prime x g prime x. But these two are equal. We've already seen this in step 1 above. So this is 2 times expected value of fx L gx plus expected value of f prime x g prime x. Okay, and this is 0. That's first step here. So this guy here is equal to minus this. Okay. So that completes the proof. So this implies the claim holds. So expected value of fx L gx is equal to minus expected value of f prime x g prime x. Okay, so we worked hard for this last differential inequality, but we are there. So many of these steps are very general, and this proof is very sophisticated. It just looks like some manipulations, but the way the things that we have been differentiating and this differential equation that we wrote, we exploit a lot this structure in the distribution, the Gaussian distribution. We realized that we saw our distribution as a process. Okay, although we wanted to work with a single t, but we saw it as a process which evolves like this. In fact, this process has a name. This is the OU process, and this OU process is a Markov process, and it has associated with this process is this semigroup operator WT, this semigroup operator WT, and with this Markov process we have this nice infinitesimal generator Lfx given by f minus x f prime x plus f prime prime x, and any such infinitesimal generator and the semigroup must satisfy this Kolmogorov equation. So once we have this relation and once we have this formula, we have this nice formula. This is only true for Gaussian case. For this particular OU process, we have this nice formula for the OU process. Okay, for fx L gx, and basically we use this formula. This is, I think, called the integration by part formula, and we use this one here to get this equality. And essentially it is this integration by part formula which establishes the equivalence of log Sobolev inequality and hypercontractivity. Note that we have only shown that log Sobolev inequality implies hypercontractivity. Now for the other way around, we have to have any arbitrary function here, and we can start with our favorite function fx by we can start with our favorite function f, and it will but we should be able to express that function f in this form, in this particular form, and that can be done. That can always be done. I think if you set this I think we can do that by even taking this limit t to go to 0. I think maybe we'll be able to do that, right? But that's a small technical part. There's no big deal about that part. The fact that the fact that log Sobolev inequality implies this is the critical part of the proof, and and yeah. So to summarize, we have seen that the Gaussian log Sobolev inequality is also equivalent to Gaussian hypercontractivity, by the way, which also gives you the Gaussian strong data processing inequality and all the other implications that we saw for hypercontractivity. So log Sobolev inequality for Gaussian case is indeed very powerful. In fact, many of the results that we saw for the Gaussian case, not the Stamps inequality, but the equivalence between hypercontractivity and log Sobolev inequality also hold for the binary symmetric case. So instead of this Gaussian, if you had, so here we were adding this Gaussian noise. That's how our correlation was. But you can have a binary symmetric channel where you have some x and you flip it with some probability. Let's say you have a uniform 0 1 valued random variable x, and you flip that bit with some probability and symmetrically for both 0 and 1. That's a binary symmetric channel. For that also we can establish an equivalence between Gaussian, but an equivalence between log Sobolev inequality and hypercontractivity. Okay, this concludes this lecture, and from the next lecture onwards, I think Aditya, actually no. So I'll see you in the next lecture, where I will talk to you about some more inequalities, and I will describe the I will further discuss the connection of log Sobolev inequalities to concentration bounds, and I'll also discuss the I will revisit the transportation information inequalities. Okay, see you in the next lecture.